Hello, in our last video we proved that each of the midlines of a triangle is parallel to and half the length of the one of the sides of the triangle. And so the midline triangle is similar to the uh, original triangle with a factor of 1/2 for the proportionality constant. Next, we're going to look at something else. We're going to look at related to it. A median of a triangle is a line segment with one endpoint at a vertex of the triangle and the other endpoint at the midpoint of the opposite side. So each triangle will have 3 medians. And once again, I'm going to have a GeoGebra investigation task, which will discover some properties of medians and what's called the centroid of a triangle. So as usual, you need to complete this task yourself before you keep reading on the notes or watching the video. So I strongly encourage you to do this task yourself. You will learn a whole lot more than just watching the video. Okay, and then once you've done it, then come back to the video. So if you could open back up the construction from the previous task where we constructed a triangle with its midline triangle, construct each median and make separate hide show checkboxes for each of them. Hide one of the medians, show the other 2 medians, and let P be the intersection of the visible medians. Next, show the other median. What do you notice? Manipulate the vertices to test your conjecture. The intersection point of the medians is called the centroid of the triangle. Now show midline XY and medians AX and BY. Hide the other medians and midlines. And what can we say about the triangles that you see there? Triangle ABP and triangle XYP. Well, test your conjecture out and prove it. So what does this say about the relationship between the length XP and the length PA and between the length YP and the length PB? Now hide the midline XY, line segment XY, and median, line segment BY, and show the midline, line segment XZ, and median, line segment CZ. Apply the same arguments to get the same results and use that results to show that the medians actually intersect at a single point, the point P or the centroid, and then carefully state your results as a proposition. So if you would, please complete this yourself now and then come back when you're finished. Press pause now. Well, I really hope you did this on your own. Let's take a look at what this is going to look like. So I've done the thing here. Again, here we have a triangle. I can show the midlines. I can show the midpoints or not. I can look at some links. Okay, and then here are the medians. There's one, and there's one. Okay, and one thing we notice is the medians all cross in the same place. So isn't that cool? That's a very cool result. So we're going to actually prove that result. We may have actually seen this in an earlier video when we just talked about multiple types of triangle centers, but we're going to actually prove it now. So let's see which one. I think I said to look at YZ and then the other 2 medians like this that share the endpoints. So get one of the medians and then the 2 of the medians, and then take the midline that connects the 2 vertices there. The 2 midpoints there that are endpoints of the 2 medians. Okay, now we got 2 triangles here. First of all, you can see you've got a pair of vertical angles here at P. We've got we already proved that this is parallel to this. So by the Z property, alternate interior angles of a pair of parallel lines here that are cut by this transversal have to be congruent. So you've got a congruent angle right here at C, angle BCZ, and angle YZC. So now these 2 triangles have 2 angles that are corresponding and congruent. Angle Z corresponds to C, P corresponds to P, and therefore those 2 triangles must be similar by the angle-angle similarity theorem. Okay, so we have that. Well, what's the proportionality constant? Well, this side corresponds, YZ, this median corresponds to the side CB. Okay, actually it's the other way around as far as the order. Z and C correspond, and Y and B correspond. But these correspond, and notice that we already know that depending on which way we go, the factor is 2 or 1/2, depending on which one's the original one. Okay, so I've got all that written up here in a proof. Okay, so therefore we know that XP is 1/2 of AP, but we also know that P is between A and X. So AX is AP plus PX. But now PX is, let's see, PX is, I said this wrong. PAP is twice XP, or PX. So this is another PX. And so AX is 3 times XP. And so XP then is 1/3 of AX. That is stated correctly. Similarly, the same result holds on this side too. So YP is 1/3 of BY. Now let's just consider it a different one. Let's look at the midline where we have XZ and then these two medians, CZ and AX. Well, it's exactly the same setup. The way we labeled the letters didn't really matter. As long as that's a midline and these are medians, we're going to get exactly the same result. So let's call the intersection this time P prime, okay? Potentially different point. But it's not, because we see that the distance from X to P prime has to be 1/3 of the X distance to X to A, but we already know that P, the intersection that we found up here, is 1/3 of the way from X to A. And so P prime has to be the same as P, and that shows that all 3 of the medians must intersect at the same point, P. So P prime is P, those are the same point. Okay, and of course the same thing works for the other one. So we got all 3 these intersecting at one spot, including the other picture there of the other ones as well. Okay. So here, whether we start with XY and work it out, or XZ works out the same way, or if we start with YZ, either way it works the same. Here you can actually see, if I click on the, let's go back to the dynamic version here. If I look at the links of the medians and the midline links, there's the side links. There we get a half. We saw that relationship last time. But if we look at the links to the distance from the midpoints to the centroid, you can check out the numbers here and see that it works. If you take 1/3 of these links, you get these links here. Okay, the arithmetic works out there, and it stays the same. If we move this around, the numbers change, but we still got that same 1/3 relationship. Okay. Now, for those of you who have studied some calculus, you may recall in calculus 2 and 3 that you calculated and interpreted a centroid of a planar lamina as a center of mass or a balance point. Now we're going to investigate areas in a couple of chapters, a couple of playlists down the road here, and we will show that the centroid of a triangle as we defined it has the center of mass property, but we're going to do that without calculus. okay? And thus the concept of a centroid or center of mass of a planar lamina then is the extension of the concept of the centroid of a triangle. So we'll come back to centroid a little bit later.